In this video, we're going to see an example of transformation from two random variables to two other random variables that are functions of the first two. So here is the problem we have. It's given that x and y are two uncorrelated random variables. The distribution for x is Gaussian with zero mean and variance is sigma squared, and the variable y has the same distribution. Now we have two new random variables. R is a function of x and y given by this function, and theta is another function of x and y given by this. And we need to find the PDF of R, theta, and then also check if R and theta are independent. To solve this problem, we're going to use this approach. Anytime we have two random variables, x and y, and then we are making two functions of x and y, g of x and y and h of x and y, and calling the function w and z, which will be two new random variables, then the joint PDF of w and z is given by this formula. So where we have this sum. And this pxy is the joint PDF of the two existing random variables. We have xi, yi's. So x1, y1, x2, y2. These are the roots of two equations. The first equation is the function, the equation is w equals g of xy. And the second one is z equals h of xy. If we solve these two equations for x and y, then we get the solutions for x and y in terms of w and z. And the solutions, there could be multiple solutions. We call them x1, y1, x2, y2, x3, y3, depending on how many solutions we have. So we have to plug in the solutions for x and y in the joint PDF. And then we also need to evaluate a matrix J, which is called the Jacobian matrix, defined as shown here. It's a matrix of first derivatives. And then we need to take the determinant of that matrix, find its magnitude, and plug in the expressions for xi's and yi's. So for our problem, the first step we're going to take is find the derivatives for the Jacobian matrix. So remember, the equations that we have are g of xy is the square root of x squared plus y squared, and h of xy is the inverse tangent of y by x. Now, the first derivative we have is, so we're differentiating g with respect to x, and g is this square root. So we have to apply the chain rule here, and the formula we're using is for any square root. When we differentiate this, we get 1 by 2 square root of a. And so using that formula and applying the chain rule, we get this expression, and simplifying that, we get this. And in a similar manner, we can differentiate g with respect to y, and it's quite similar. And simplifying the derivative, we get this expression for the second derivative. The third one is differentiating h with respect to x, and we have inverse tangent. So for this, we have to use the formula. Derivative of inverse tangent is 1 by 1 plus a squared. So applying that formula and chain rule, we get this expression. And simplifying that, we get this. And the fourth one is quite similar to the third one. This time we are differentiating the inverse tangent, but with respect to y, applying the chain rule again, and simplifying, we get this expression. So we have four derivatives now, and collecting them, we can form the Jacobian matrix. This is the matrix, and we take its determinant, which will be this times this minus this times this, will give us this expression. Then we need the solutions of the two equations that we have. R equals g of xy and theta equals h of x and y. So we have these two equations, and solving for x and y, we get just one solution, and that is r cosine theta and r sine of theta. We're calling them x1, y1. So in our formula, instead of this sum, we have just one term because just one solution is present. And the joint PDF of the two new random variables r and theta is given by this. All we need to do now is take the expression for the joint PDF of xy and plug in the values for x1, y1. And we're going to do the same thing to the determinant of magnitude of the determinant of the Jacobian matrix as well. Okay, so the joint PDF of x and y, since they are independent and normal, their joint PDF is given by this. We're taking the individual PDF of x, individual PDF of y, and multiplying them because they are independent. We can do that to get the joint PDF. And we can combine these two exponentials to write them as one exponential like this. And in this expression, we're plugging in x equals r cosine theta, y equals r sine theta to get. That means we're evaluating pxy at x equals x1, y equals y1, which will be this. And simplifying using the identity, cosine square plus sine square is 1, we get this. And then we also need to evaluate the magnitude of the determinant at x equals r cosine theta, y equals r sine theta, right? So plugging in that, we get 1 by r. So finally, the joint density function of PR theta is given by this. And note that r is going to vary from 0, less than infinity. Theta is going to vary from 0 to 2 pi. Once we have the joint PDF, we can get the marginal PDFs by just integrating out the unwanted unwanted variable. So for instance, from this, if we want to get the PDF, just r, so we need to integrate out theta. That means we will integrate this over the entire range of theta, that is 0 to 2 pi. And that means all this is going to be a constant since we're integrating with respect to theta. That can be pulled out of the integral. And integrating this, we get 2 pi, which will cancel the 2 pi over here. And this, a function of r, this is going to be the PDF of just r. And the range for r is greater than or equal to 0. And we can also find the PDF of theta in the same way. We would have to integrate out r. So that means the range for r is 0 to infinity. So we can pull out 1 by 2 pi. We're left with this. And remember that, so now what we are integrating is actually the PDF of r, which we already found over here. And integrating the PDF of anything over its entire support, in this case, it is 0 to infinity, always gives us a 1. So we're left with just 1 by 2 pi. That means the marginal PDF of theta is 1 by 2 pi, and its range is 0 to 2 pi. So it happens to be a uniform distribution. So finally, what we can see is that if x and y both have normal distributions with 0 mean and the same variance, and they are uncorrelated, then the joint PDF of r and theta, which are defined like this, is given by this expression. And the PDF of r, this is Rayleigh distributed, it's given by this. And the PDF of theta, it is uniformly distributed, it is given by this. And also we can note that this PDF can be factored into the marginal PDFs of r and theta. Since this is true, we can also conclude that r and theta are independent.